how to determine and communicate homomorphisms. We are facing now the same problem that we had for subvector spaces. The issue of finding homomorphisms with the properties we want and then to communicate them. First, notice that for any vector space V and W, there always exists at least one homomorphism from V to W, namely the zero application. So if we take any vector in the domain and we send it to the zero vector in the codomain, we can readily prove that this is indeed an homomorphism. Therefore, there will always be one between any two vector spaces. There is no assumption here on V or W. However, we will soon see that as soon as W is a non-zero vector space, so it is a vector space that is not reduced just to the identity element, it will have at least dimension 1, there will always exist infinitely many non-zero homomorphisms from V to W. There is a striking analogy between expressing a subvector spaces and homomorphisms. The former had two kinds of expressions. One was what we called the expression in coordinates, which was considering the subvector spaces simply as a set, and describe it as a set, opening the curly brackets and listing all the elements that are inside the set. The second expression was what we called parametric, and it was the one that was actually using the algebraic structure of a subvector space. A subvector space is not just a subset of a vector space. It's a subset of a vector space with algebraic structures on it, which are induced from the big vector space in which the subset is embedded in. We went actually through these differences in expressions very carefully in the exercise 1.3, so I refer you to check this out. Talking about the analog of the in-coordinates expressions, but for homomorphisms, we can say the following. One can prove that any set theoretic map from Rn to Rk can be written as f applied to a generic vector in the domain given by the coefficients x1 through xn equals this k-tuple of functions f1 depending on x1 through xn, f2 depending again by x1 through xn, and so on up to fk. Each of these functions gives the coordinates of the images of f. It has to contain 4 k real numbers, since it is the codomain is in Rk, so we need k real valued functions f1 through fk. Moreover, f is linear if and only if every fi is linear. For a real valued map, being linear means that the image of a generic point in the domain is a linear combination with certain coefficients of the variables, and this must hold for every component of f, from f1 through fk. If f is a set theoretic map between not necessarily Euclidean vector spaces, remember that in the previous case, when we had an in-coordinate expression of f, we were assuming that the domain and the codomain were Euclidean spaces. In this case, we are not assuming it. And actually, we are not having any assumption on V and W. And the result is that, in general, we cannot really express f. But if we are willing to assume a very mild assumption in our course, which is the vector spaces domain and codomain to be finite dimensional, then we do have another expression of f which is not in coordinates, and it works for any vector space V and W. So creating or expressing f is equivalent to writing the images of a basis of v. So I fix any basis of v, and I pick certain vectors here in W just randomly, and this allows me to construct a homomorphism f, which will send the vectors of the basis of v that I've chosen to the vectors that I've chosen in W, and then from just the action on the basis of v, I will be able to expand the whole f on the whole vector space v. Let's see how to do this. Let's assume to have the images of a basis, elements of a basis of v. So I have f of vi, and I have no assumption whatsoever on what these f of vi's are. This is a very important remark. F of vi's are just any random in this case, any generic element in the codomain. They can be all vanishing, they can be all the same element, they can be whatever. Doesn't matter at all for the argument I'm going to do. These are just n randomly chosen elements in the codomain. So if we have these n randomly chosen elements in the codomain, we can define f on a generic element in the domain. Let's call this generic element z. And since it is a generic element in the domain, certainly there will be a unique linear combination that will express z in function of the basis that I fixed in the domain vi. Let's call alpha I the coefficients expressing z in function of the vi. Then, with this data, with this alpha I can define f, which so far is just acting on the elements of the basis vi. I can define f on any element in the domain z by the following formula. I take a linear combination of the images of the vi's using the same coefficients as the ones I have obtained by this expression here. So this creates a map f that goes from all v to w, which is really shown to be linear. This map with this definition is linear. Vice versa, let's assume now that we already have a linear map f from v to w, and let's show that f is completely determined by its action on a basis of v. So before we did not have f, we defined f extending any set theoretic map from a basis of v to any elements in w. Now we show that starting from a linear map f from v to w, all v to w, we see that f is completely determined by the images of any basis of v. So the argument in A shows that f is uniquely determined by the vectors f of vi. Since any other vector z different from the vi must go to the following image, linear combination of f of vi's with coefficients alpha I, where alpha I is the unique linear combination expressing z in function of the vi. There is no escape to this. So once f is assigned on a basis of v, then all the other vectors are forced to go to this vector here, this linear combination. Or in other words, if there are two maps, linear maps, f and g, that act in the same way on a basis of v, then they must coincide. F and g must coincide as maps, meaning that every other vector in the domain must go to the same vector in the codomain. F of z will be equal to g of z for any z. So summing up, we can express or create an homomorphism f from v to w in two ways. One, which we call again in coordinates, necessarily we'll have to assume that both y and w are Euclidean vector spaces of finite dimension. And the expression is the one that you wrote before. We take a generic vector R in Rn with coordinates x1 through xn, and its image will necessarily be of the form f1 of x1 through xn, where f1 is a linear function from Rn to R, and then f2 of x1 to xn, and so on up to fk of x1 through xn, where all the fi's are linear maps from Rn to R. Then there is the equivalent of the expression, parametric expression for subvector spaces, which in this case we don't call it. So f, if we don't express f in coordinates, we don't really have a name for this expression. There is no expression, parametric expression for a homomorphism. But the concept is very similar, because we reduce the expression of f to the choice of a basis of the domain and the prescription of where these elements of the basis go in the codomain. We can express f by providing the images of a basis vi of v if v and w are any finite dimensional vector spaces. Unlike before, when v and w are not assumed to be Euclidean, this is the only way we can actually communicate or determine an homomorphism between v and w. The option of coordinates exists only in the case the vector spaces, domain and codomain, are Euclidean. Just like for the expression of subvector spaces, each of these two expressions has its own advantages and disadvantages. Typically, it is easier to create an homomorphism by assigning the image of a basis. This because we have the freedom of choosing the basis. And normally this basis is chosen according to the problem we are dealing with and the information we have on f. Whereas in coordinates we have no such a choice. In coordinates the expression is unique and we cannot customize it to the spatial situation we are considering. However, it is easier to compute images of vectors other than the one of a basis if we can have the homomorphism expressed in coordinates. This cannot always happen, of course, because if the vector spaces are not Euclidean, we cannot have this expression, but in the case they are Euclidean, we do have this option, and this is the preferable option if we want to use the homomorphism afterwards. Once we determine it, and we want to use it to compute, say, the image of 1,000 of vectors or 1 million of vectors of the domain, then it is much more efficient to change the expression of the homomorphism from the image of a basis to the expression in coordinates.